Welcome everyone to my course Formal Methods for System Verification. In today's class, we will learn how we can construct the ROBDD directly from a given proposition formula. So, as I discussed in the previous class, this ROBDD is a canonical representation and is very important in the context of verification and circuit optimization. So, we have also seen how we get the ROBDD, how to construct the ROBDD from a function. But we have also seen that constructing the initial BDD and then you construct the ROBDD from that by you applying the 3 reduction rule is makes no sense, right. So, we should construct the ROBDD directly from the function. Okay. So, this effectively I have already discussed about this level, variable, var, low, high and value corresponding to a BDD, right. So, you think about that this is my VDD. So, every node has name, right, V1, V2, V3 and so on. So, var of V1 is basically x1, var of V3 is basically x2 and so on, right. So, then you know what is level. So, this is the level 1, this is level 1, this is level 2, this is level 3. So, I have already discussed that in a ordered BDD each level represent one variable, right. So, any node in this level will be x2, any node in this level will be x3 only. Since there is no x2 here, so I just keep it and put it x3 here, right. So, this is the level. Then we have this low high that I already talked about, this left and right or low high whatever you say. So, low of V1 is x3, then high of V1 is x2, right. So, effectively this low or left and right, right. So, that way usually there is no left and right, you usually have 0 and 1. So, it is better to maintain the low and high. Then we have the value. Value is basically corresponding to the terminal nodes. So, here this value of this node is 0 and value of this node is 1, right. So, if this node is say V5 and V6, so val of V5 is 0, val of V6 is equal to 1. So, we just keep this terminology no, so that we can develop the algorithm. So, there are two key operations we will learn before proceed how do you construct the ROBDD directly. The first one is called restrict and the next one is called apply. So, the restrict is very simple, it is that you have a BDD or you think about a proposition formula and I am restricting this particular BDD with a particular values fixed value, right. Think about I have a BDD B which has say variable x, y and z and then I want to restrict that very BDD with x equal to 0. So, I will write this way that B where x equal to 0, I will see what is the resultant BDD. Similarly, if I want to restrict the BDD B with x equal to 1, I will write like this. Okay. So, this is the restrict operation, but just to explain, let us say I have this BDD. So, here little bit of problem. So, x3 should be the next level, right, because this cannot be in the same level. So, this is the BDD I have constructed in the previous class, right. So, now if I want to restrict this BDD where say x2 equal to 0, x2 equal to say 0, okay. So, then I am writing this. So, what will happen? Effectively this becomes 0. What does it mean? This does not exist. So, this only exists this and this variable also is 0. So, what will happen? I will just connect this directly to this node, right. This is how the restrict operation. So, what I have done is basically I just connect the x1 of 1, the high of x1 directly to 0 node, right. This is the restriction in a BDD. So, even given any BDD, you can actually restrict that particular BDD for a very specific value. For example, if you say here I just put B restricted x1 equal to 1, what does it mean? So, this part of the BDD has no value, right. This is x equal to 0, x1 equal to 1, 0. So, I will only consider this BDD. So, this will result in x2 0 and 1, 0 and 1. So, this is the only this part of the BDD, right. So, this is you can do. Similarly, if you think about I have a say x1 and x2 or not of x1 and x3, right. So, I have this function, right. Now, if I want to restrict this function by x 1 equal to 0, What does it mean? If I put x1 equal to 0, so I will put 0 here, x1 equal to, so this become false, and here x1 equal to 0 means this become true. So, this basically result to x3, right. So, if I take this function and I restrict this function with x1 equal to 0, it result into a value x3. So, whether this is a BDD or a Boolean expression, I can restrict that function to any variable and get a reduced size BDD or reduced size expression. Okay. So, the restrict we understood. The next one is apply. So, this is generic expression. So, you think about that I have two BDD and I apply any operation, right. So, you basically have a BDD B1 and you have BDD BD2, I want to do AND of these two BDD2. How can I do that, right? Or you think about I have BDD 1 and I do a OR of these two BDD2. So, basically the apply operation is that you have two BDD already and I want to combine them with a Boolean operator. How can you do that? So, that is the apply. Okay. The same thing you can think about a function also, right. So, you have a Boolean function, two function f1 and f2 and I want to combine them with a Boolean operator. Okay. So, in case of BDD, this is little bit interesting. How can you do that? Because these two BDD can be different, right. And obviously, there are many things happens here. These two BDD can have completely different variables, still you can combine, right, or they have some variable common, right, and some variable is uncommon, right, or they have exactly same set of variables, all can happen. So, combining these two BDD with some variable or, but their ordering is same, right, is something we learn through this apply operator. What do you mean by ordering is same? So, suppose you have a BDD which has a variable x1, x4 and x5, right. Another BDD B2 which has say x2, x3 and x4, right. So, you can see here x4 is common, right, other variables are not common, but I can consider the actual variable order is maybe x1, x2, then x3, then x4, then x5. So, that means the order of the variable is x2, x3, x4 here and this is x1, x4, x5 here. So, they are basically a global order maintain both BDDs, otherwise we cannot apply the apply operator. So, if we know how to apply this apply operator, I can combine any BDD and then I can construct the bigger BDD, right. This is the direct construction. So, effectively I construct the original ROBDD of the bigger function by combining smaller BDD together, right. Because if I know how to combine two BDD, I can apply any operator, right, it can be AND or not anything and I can combine to a bigger BDD, right. So, let us learn how this apply operator can be done. So, in the BDD, so as I mentioned that there are say two BDD B1 and B2, their root nodes is B1 and B2 and these are the cases can arise. Okay. I talked about the variables there, but remember they have the similar relative variable order maintained, right, the example I have given in the previous slide. So, if both of them is terminal node, that means the terminal cases. So, one BDD is 0, one BDD is 1. So, if you do a AND of this, I will get a 0, right. If I OR of them, I will get 1. So, if they are terminal node, you just apply the Boolean proposition logic and you get the resultant BDD. That is very obvious case. Now, I have two BDD and they have the same root node. So, this variable, this BDD also start with x1, this variable BDD also start with x1. That is a good case, right. So, if you have two BDD have the same root node, the first level node, then what will you do, right. This is case 2, or it can happen, it has say this BDD root node is less than the root of between the variable order. Example of this x1 to x5 that I have talked about in the previous slide, you can think about that this BDD B1 start with x1 and BDD B2 start with x3. So, that means BDD B1 start with a variable, the root node is less than in the order of what is the root node of B2, it is come before that root node. Okay. This is another scenario. And the opposite scenario is the other one, that B1 is has a B1 has x2 root node and B2 has x1. So, that means root node of B1 is greater than of root node of B2 in the order. This is the opposite case of this. So, if this fourth scenario can happen, this is the only scenario can happen. And if this scenario happen, how do I combine, right, that is the question. So, these rules we will understood. So, as I mentioned, the terminal cases where both BDD are terminal node, you can just apply directly, right. So, if one BDD is 0, one BDD is 1, if I apply the AND operator, I will get output 1, if I apply OR, I will get 1. So, that I already explained, this is obvious, right. Now, if the case 2 or scenario 2, so I have 2 BDD and they have the same root node. So, that means this also start with x1, this will also start with say x1. How do I combine? So, I will apply this Shannon expansion rule here, right. So, what I will do, look it carefully. I have 2 BDD B1 and B2, the operator I am using this one, this can be AND or anything. So, what I am saying that this is equivalent to not of x and then say the root node is basically x, okay. The root node is basically x in this case. So, I am saying that it is equivalent to not of x1 into applying this operator recursively, because apply is a function, right, where I restrict B1 with x1 equal to 0, x equal to 0 and B2 also x equal to 0 and I apply the same operator, or I put x1 x, that means x equal to true, and then I put the apply operator on this restricted BDD, right. So, this is B1 restricted by x1 equal to 1, B2 x equal to 1 and then apply the same operator. So, this is a recursive one. So, what I am saying that to combine these two BDD B1 and B2 with the operator say the circle 1, to apply here on these two BDD, I am saying that I restrict the BDD B1 with x1 equal to 0, BDD B2 with x equal to 0 and I apply the operator, same operator in this smaller BDDs, right, or I will apply this operator with B1 restricted to x1, B2 restricted to x1 and I apply the same operator, and this I will combine with x and this I combine with not x, and this will be OR of this, and this is very well known in Shannon expansion. In reality, if you think about a BDD perspective, what I am effectively doing here, I construct this x as the root node because I have considered x here, and if it is 0, right, if it is 0, that is not x, then I will put this part here, right. So, whatever I have written here, I put it here, and whenever x equal to 1, that means this, then I put this part here, right. This is basically the apply operator. So, I will put it basically apply here with this and has and apply this and has, right. So, I already got the root node of the resultant BDD which will be x, and then I get a smaller BDD here because I am restricting B1 with x equal to 0 and I have already shown that will reduce the formula greatly, and then I will apply B2 x equal to 0. So, this is x actually, right. So, then I will get the formula, and then I will recursively apply BDD on the smaller formula and I will keep doing it, right, and finally reach to the terminal cases, the 0 1 cases, the rule 1, and this is how I will get the resultant BDD, right. Similarly, the rule 3, where now once you understand the rule 2, the other 3s are very simple. So, here I am saying the root node of B1 is less than in root node of B2, right. So, for example, let us say this is say x1 and this is say x2 and say the root node is x1 now, okay. Remember, since we are following the same variable ordering in B1 and B2 and x1 coming before x2 and the root node of B1 is x1 and root node of B2 is x2, it means B2 does not have x1, because if B2 has x1, this should be the root node because that is the order I am following, right. So, it means x1 does not occur in B2, okay. So, if you have this scenario, how do I combine? So, it basically the same process. I have the root node, I will set x1 because x1 is the first node, and because x1 does not occur in B2, no point applying restriction on x1 because it will not change anything, because even if I apply restriction on B2, say B2 restricted x1 equal to 0, it is B2, right, or B2 restricted x1 equal to 1, this is B2, because B2 does not, x1 does not occur here, it will not simplify it. So, I will use the same formula, but only thing is that here I will, instead of writing B2 x2 equal to 0, I will just directly write B2 because it is same thing, right. This is what I have written here. So, if I apply this B1 B2 with the operator this with the root node is x1 now, because x1 is coming first, I will apply B1 restricted x1 equal to 0, but B2 here, right, because B2 will not be reduced with x1 equal to 0. and B1 restricted to x1 equal to and B2. The same formula previous, but just I am not restricting B2 to x1 equal to 0 or 1. If you see in the visualize in the BDD form, I will create a root node with x1, and if it is 0, I will apply here the rule with B1 x restricted to 0, B2 and the operator, or I will apply B1 restricted x1 equal to 1, B2 and the operator. So, I will get much simpler formula here, and I will keep applying the same thing, right, until I get the root node. And rule 4 is just opposite of the rule 3, because here I am saying that root node of B1 is greater than the root node of the B2. That means B2 has x1 and this is has x2. So, that means this does not have x1. So, now I will not restrict B1, only restrict B2, right, that is the only changes here. So, what I am doing here is, if I am applying this, so and say the root node is x1, right. So, x1 here. So, I will apply x1 equal to I will apply B2 to x1, because B1 does not have x1, and then this will be x1, and again B1 B2 I will apply x1 equal to 1, right, where x1 is the root node of B2. So, now essentially I will create a root node x1. If it is 0, I will apply B1 does not have x1, B2 x2 restricted to this and this operator, and I will apply B1 B2 x2 equal to 1 and the operator, right. This is the rule. So, this I have to apply repeatedly, because this is another BDD operation now. I will keep doing this to construct the final BDD. So, see I have not construct the original BDD, the initial BDD here, right. So, things will be clear when I consider a simple example. So, let us take the same example that I have taken in my previous class, where I try to construct the initial BDD and then I apply the 3 rules to get the reduced BDD. So, here, so I have this order. So, let us say this is my B1, right, this is my say B1, this is my B2, right. So, I will show the example with some formula first, and also I will show that how to combine 2 BDD also later. So, this is my B1 and this is B2, and this operator is basically the operator I was talking about earlier is OR, right. So, I am basically doing BDD OR operation of 2 BDD, which is this and this, right. So, B1 is this and this, and let us say the variable order is x1, x2, x3, this is the order. So, the first level is x1, then x2, then x3. So, I will apply BDD where this is the BDD of x1, x2, this is the BDD of not upon x2, x3, and the operator is OR. So, what is the rule here? The rule 2 will be applicable, because both of them has x1, right. So, I will apply rule 2, because rule 2 say that both BDD has the same root node. Then you see now things will be very simple. So, what I am doing here, x1, if it is 0, this is the formula which I restrict with x1 equal to 0, and this is the formula which I will put x1 equal to 0. Similarly, this is the formula I will restrict x equal to 1, or this is the formula which I restrict x equal to 1. So, what will happen here, if you put x1 equal to 0 here, this will become 0, and then this become this is, if you put x1 equal to 0 here, this is 1. So, this entire thing will reduce to only x3, right. This is 0, this is 1. So, this will become x3, and similarly here if you put x1 equal to 1, so this will become x2, and if you put x1 equal to 1 here, this is become 0. So, this will become false. So, this become x2. So, effectively this means nothing but x1, if it is 0, I have to construct the BDD of x3, and if it is 1, I have to construct the BDD of x2, as simple as that, right. Now, again I consider this x3, I can consider x3 as 2 formula, that x3 dot 1. So, this is my BDD B1, this is my BDD B2, and I can apply the same rule. Similarly, for x2 I can consider x2 equal to x2 dot 1. So, this is my BDD B2, this is my B3, and the operator is AND, right, and I can apply the same rule. So, what rule will be applicable here? So, the root node is x3, here this is 1. So, the rule 3 will be applicable, right. So, with this rule 3 I can combine again to get the resultant BDD, and I can combine repeatedly in both sides and get the BDD, right, just to completeness. So, what I did, I get this, right. So, this is the BDD I got. Now, so if I construct the BDD corresponding to this, so now this is my B1, this is my B2, right, and I can apply the same rule. So, now B1 is x3, B2 is 1. So, I am applying the BDD of x3, BDD of 1 and then I am combining them with AND operator, right. So, this is rule 3, you can think about that x3 is the root node of this, rule 3, rule 2 anything is fine because other root does not have any node, right. So, what will happen here? So, this part I am doing now, right. So, what is happening here? So, x3 if it is 0 then I am restricting this x3 to 0 and 1 because 1 does not have x3. Then here what is happening? So, this will be x3, right, because the root node, and now restricting this with x3 equal to 1 and 1. So, this will become, if you put x3 equal to 0, this will become 0 and this is become 1. So, effectively I got x1, x3 when it is 0, then this is basically a 0 node, this is a 1 node, right, 0 and 1 because this becomes 0 and 1. And same thing will happen for x2 also because it is the same thing. So, I will now put x2 and this will connect to 0 and this is 1. So, this is the BDD I constructed earlier, I constructed here also. Remember, I will not repeat any node. So, one important thing to note here, if you got any sub BDD which is same, for example, here 0 and 1, I will use them. Okay. Even internally also there is a sub BDD I construct from this side which can be reused here, I will reuse them. Otherwise, there will be redundancies or the isomorphism, right. So, so I have already shown you this. So, this is the final BDD. Here the order is not maintained properly. So, this x2 will be here, and so if I construct x1, if I put 0 I will come to x3, if I put 1 I will come to x2 and then I have 0 and 1, right. So, this is 0, this is 1. This is 0, this is 1. Okay. So, this is clear. Now, let us take a little bit bigger example so that you understand. Let us say I am checking whether I have two value a and b which is 2 bits and I am checking whether a greater than b or not. Okay. So, a is 2 bits a1 a0 and b is 2 bits b1 b0. And you know how to do this. Effectively I will check whether the MSB of a1, if this is 1 and this is 0, then this is a greater than b, right. I do not need to check the LSB. So, I will check a1 b1 dash. If this is not, then I will check if they are same, right. This is basically x naught which is effectively a1. So, this is basically checking x naught, right. So, this is basically either this will be a1 b1 or a1 dash b1 dash. So, basically either this is 1 1 or 0 0. If they are same, then I will check the LSBs, right. If a1 is 1 and b2 is 0, b0 is 0, then this is a greater than b, right. This is how we will check the thing. So, effectively I have this formula, right. The formula is basically if I write here a1 b1 dash or a1 b1 or a1 dash b1 dash, then a0 b1 dash b0 dash. So, this is the formula I want to construct the BDD corresponding to this, okay. And how I can construct this directly. Let us say I consider the variable order is this a1 b1 a0 b0, and let us say this I consider as b1 and this is the part I consider as b2, right. So, go back here. So, let me take this example properly. So, I have b1 which is a1 b1 dash and I have a b2 which is a1 b1 or a1 dash b1 dash followed by a0 b0 dash, right. So, this is the 2 BDD and I have OR, right, operator is OR, okay. So, what scenario will come here? It is, you can see here both has a1, right. So, the order is I have already talked about a1 or b1 or a0 b0. So, both have a1. So, they have the same root node. So, this is the rule 2, they have the same root node. Then what will happen? I will construct directly. So, I will have a1 is the root node and then if it is 0, then what will happen? I will restrict this one with a1 equal to 0. So, what will happen? This will become 0 or I restrict this one with a1 equal to 0. So, if I put a1 equal to 0 and this is become 0, this is become 1, right, and this part is not touched. So, it is basically b1 B1 dash into A0 B0 dash. So, this will be this part, right, and if you put A equal to 1, what will happen? I will restrict this with A1 equal to 1, which will be B1 dash, because if I put A1 equal to 1 here, or if I put here A1 equal to 1, so this is B1, this is 0, so this is B1 A0 B0 dash, right. So, this is what I will get, right. So, now I will again take this part, which is effectively means B1 dash this. So, now if I consider B1 dash A0 B0 dash, so this is my original formula. I can consider, say, this is my B1, this is my B2, okay. So, then what will happen, and my operator is AND, right, operator is AND, right. So, again I can try to construct, because this has B1 and this does not have. So, this is the rule 3, right. What will happen? So, I will consider B1 as the root node, and if it is 0, then what will happen? I will restrict this B1, which is B1 just equal to x equal to 0. So, this will become 1. So, this will become 1, and if this part does not have B1, so this will remain as it is A0 B0 dash. So, this is the BDD I have to construct here, and if it is 1, so if it is 1, so B1 dash will be 0, right. So, B1 dash will be 0 means the AND of both of them will be 0. So, this will reach to 0, right. Now, if you consider this part, which is B1 dash or B1 A0 B0 dash, okay. So, now I can consider, let me just cross check this one. So, if I put A1 equal to 1 here, then what will happen? This will reduce to B1 dash, and here A1, if I put A1 here, this will become B1 A0 B0 dash, okay. And say this is my B1, this is my B2, and operator is OR. Now, if I try to construct here, so I have B1 here, I also have B1 here, so it is rule 2. So, I will have B1 here root node, and if it is 0, if I put it at 1 here, so this will become 1, or, and here I put it 0, so this will become 0. Now, this will become 1 effectively, and if I put 1 here, so this will become 0, because the 1 complements 0, or this, and now I have B1 which is 1. So, this will become A0 B0 dash, right. I have to construct the BDD of this. You see here, I have already reached to the terminal node here, and you see here this is A0 B0 dash, this is also A0 B0 dash. So, I will not construct 2 BDD anymore, I will construct only 1 BDD, right. So, I will only construct for A0 B0 dash, and I will reuse both of the places. So, for this, if I assume this is my B1, this is my B2, and the operator is AND, then so here A0 is the root node, because and it is rule 3, because it does not have A0, right. If you put 0 here, A0 equal to 0, so this will become 0, and if you put 1 here, this will become B0 dash, right. So, which is effectively the BDD is A0. If you put 0, this will become 0, and if you put 1, then B0, and then effectively B0 dash. So, if you put 1, it will be 0, if you put 0, if you put 1, then it will be 0, and if you put 0, this will be 1. So, this is the BDD corresponding to this. So, what will be the final BDD? I have A1, if you put 0 here, I will get this BDD, which is B1, and B1, if you put 0 here, I will get this BDD, right, which is A0, then you have B0, and then you have 0 and 1. If you put A equal to 0, I will come here. If you put equal to 0, I will come here, and if I put 1, I will go there. So, this is the BDD I got here, and so I got I am going to construct this BDD, right. This is the BDD, and if you put B equal to 1, I will go to 0, right. So, this BDD is constructed. So, for this BDD, this is the BDD. So, if I put 1, I will go to B1, and when I put B1 equal to 0, I will come here, right. and if I put B1 equal to 1, I will go to this BDD, which is basically this, right. So, this is the final ROBDD I construct corresponding to this the checking comparator for two bit number, right. So, I have already shown you how it will work, right. So, this is the final BDD I will get for this. Okay. So, similarly, if you have two BDD, you can also apply this operator, right, just to quickly show you that. So, suppose I have BDD for this, which is this one, and I have not of x2, this is the BDD, right. Now, I want to combine them with OR, I want to OR of them. So, it is a very simple thing. What I will do, I will rest. So, if I try to do that, their rules, their root node is different because this is x1 and this is x2. So, this is rule 3 and x1 is coming before x2, right. So, what will happen? I will construct this BDD of x1, then if it is 0, what I will do? I will try to do the apply of this BDD, where if I put x1 equal to 0, I will get only this BDD, right. And if I, and here this is the same BDD. So, if I do this and this, these are the same BDD. So, I will effectively get x2, then 1 and 0, right, whatever this BDD is 0 and 1. Similarly, if I put x equal to 1, then I will get this BDD and this BDD, and if I combine them, these are the x2, this is basically 0 is 0, 1 is 1, 0 is 0, 1 is 1, it is basically complement, I will get 0 directly, right. I will show you step by step. So, what I am in the left child x1 equal to 0 means apply B1 restricted x1 equal to 0, B2 OR, and the right child or the high child is basically x1 equal to 1 means B1 apply x equal to 1 B2, right. This is what logically I will do. So, effectively this B1 is restricted is this and B2 is this. If I combine, they are the same thing, I will get this BDD, right. And the rule 2 for both roots x2 rule 2 is applied. So, because I can actually, I just draw it like this, but you can actually do the same thing. So, here I have this is the BDD, this is the BDD, and I have to do the OR operator. So, both of the same root. So, this is the rule 2 applicable. So, I will just do x equal to 0. So, I will get 1, x2 restricted, this BDD I will restrict with 0, I will get 1. So, 1 1 on OR. So, this is the rule 1, I will get 1. Similarly, if I put x2 equal to 1, so I will get 0 here, I will get 0 here, and I will put the OR, so they will get this. This is the same BDD I will get, right. Similarly, if I do this the other part x1 equal to 1, I will get this BDD and this is the BDD, and I have to do the OR of this. You see here, if I apply restrict this with x equal to 0, so I will get 0, right. If I restrict this with x equal to 0, I will get 1, and if I do OR, I will get 1. Similarly, if I restrict this BDD with x1 equal to 1, x1 equal to 1, so I will get 1, right. And if I restrict this, I will get 0, and if I do OR, I will get 1. So, both cases I am getting 1, so I will get 1. So, the final BDD will look like this, right. So, what I am shown here, whether this is a BDD, two BDDs are there, I can combine them with apply operator by just restricting the BDD and doing recursively, or if you have given a big expression, I can construct the BDD directly using this apply rule, right. So, this is how things will work. Okay. So, I hope you understood how we can construct the BDD directly from the formula, propositional formula, or combining two BDD. So, this is an extremely useful operator, and I can actually apply this to construct any BDD from any two BDDs. Okay. Thank you.